We're going to work on another factoring pattern and shortcuts so we can have special cases to help us factor more efficiently. But this one, unlike perfect squares, is called perfect square trinomials. So what does that even mean? Well, we have to start off with things that are perfect squares, but it needs to be 3 pieces long. So a perfect square trinomial might be something that looks like this. X squared, there's a perfect square, plus 8x plus 16. And the perfect squares come in here and here, again at the beginning and end of my expression. And this would factor to be x plus 4 times x plus 4. This is the result, and I would get x squared plus 8x plus 16. So the weird part is this connection right here with that middle term. If I break this down and I factor it x squared plus 8x plus 16, the way that we're used to factoring, then I would have a generic rectangle, and I would also have a diamond pattern. My generic rectangle, I would put in my squared term, x squared, and my constant term, 16. And then I know that these pieces right here and right here, have to have a sum of 8x, and then their product would be 16x squared. Well, the only numbers that that would work with would be the numbers 4x and 4x. So I plug 4x in here and then 4x in here. You might already start to see the pattern where this 8x is related to 4x in some ways. And here I have 4x and 4x again. When I factor these, I take out my greatest common factors. I usually start with x and x. Well, x times 4 would have to go here, so it would be x plus 4 and then x plus 4 right here. In other words, I get x plus 4 times x plus 4, which can also be written as x plus 4 squared. So the first step really is in recognizing which ones fit this term of being a perfect square trinomial. So some examples would include 9x squared minus 12x plus 4. The one we just had before, which was x squared plus 8x plus 16. You've also probably seen x squared plus 10x plus 25. And they all follow a similar pattern. They all have a coefficient in front of the first one. So my coefficient is also a square number, so a squared times x squared. And then on the end, I have a constant, b squared. That number is a square number. All of these, as you can see, 25 is a square number, 16 is a square number, 4 is a square number. And so it's really this middle term here that I have to recognize the pattern. And this pattern comes from that idea that whenever I have these, I have a generic rectangle where I have the same amount here and here. So I have, in other words, 2 times whatever is in those boxes. And if I look at how those numbers break down, I end up times x plus 5, or x plus 5, in parentheses, squared. This one, 8 is 2 times 1 times 4, so this will also follow the pattern x plus 4 times x plus 4 equals x plus 4 squared. This final one, or it was actually the first one we did, 9x squared minus 12x plus 4, is a little more tricky. So I'm going to double check and figure out how does this 2abx fit the pattern of negative 12x, and if it does work. This negative sign is a little confusing, the 9 is in my way, so I want to just double check. So if this works, then a will equal 3, b will equal 2, and I need to multiply that times 2. The only problem is I have this negative sign here. So that means that in order for this to equal negative 12x, I need an x here, then one of these needs to be negative. It doesn't actually matter. Well, it does matter. What this means is that I have, I'm going to take this bottom term here because negative 2 times negative 2 will also equal positive 4. So that means that I'm going to have b is equal to negative 2. I can only tell that because of this sign. If the sign is positive, then I would end up with a plus sign in each factor. If the sign is negative, I have a negative sign in the factors. So now my a term has to be 3x. My b term is 2. I'm going to take a look at the sign. Because it's negative, that means I have a negative sign right here. So it's 3x minus 2 squared. And that is the special case of factoring perfect square trinomials. You can also just look at problem 8-47 in your book. Thank you. Bye.